This is Mrs. O'Neill for AP Chemistry, Chapter 13, Section 4, Expressing Solution Concentration. And here I have Remember Your Sig Figs, because the problems that we do in here will be the answer into the correct sig figs. And this is the section of this chapter that's going to be the math. So you should have watched the intro lesson on solutions and molarity. Here are my notes. He said that a solution is basically two or more substances really mixed together. So he talked about soda, salt water, and then he reminded you that gas is also mixed as a solution. Steel, an alloy, is also a solution. But what isn't a solution is something that's called a suspension, or something that's heterogeneously mixed. So they're not thoroughly mixed on the molecular level. And then he talked about a couple of examples. So he also talked about a colloid. And a colloid is much smaller particles, but if you zoom again at that molecular level, you're going to be able to see and that there are big pieces and small pieces. He talked about like milk. There's going to be protein pieces and other kinds of molecules in there that make it not a solution because it's not thoroughly mixed. So he gave you the idea of this Tyndall effect. And if you see the sun shining through a window and you see all those dust particles, that's really the Tyndall effect because you can actually see the particles that are in the air. So he took that flashlight and he shined it through a solution, a colloid, and what's called a suspension. So in a solution, you wouldn't even see the light. It goes right through, right? Because it's a homogeneous mixture. A colloid, on the other hand, you would see the light, and in a suspension, you would even see the particles. So again, he talked about those three different examples: solution versus colloid versus suspension, and how that light or that laser would shine through. So again, he talked about that homogeneous at the molecular level, what a solution is. He talked about water being a universal solvent. In other words, it dissolves almost everything because most things are either ionic compounds or polar, right? So if something is polar, it's going to dissolve in something that's polar like water. So in here again, he gives you some visuals. Actually, I think I pulled those off of the internet because I didn't have the visuals from his actual presentation. So again, the water is going to surround those ions. And in a covalent compound, he talked about how in the heck can we dissolve something like sugar? Well, sugar does have those hydroxyl groups, does have those OH groups. It makes it polar. So he talked about molarity. So we went from solutions to molarity, kind of a nice introduction here. And it's moles of a solute per liters of solution. So the higher the molarity, that higher the value of that number, the larger the number of moles of that stuff. So we want to remember everything is by moles for molarity, not by grams. He gave you a nice example using Mountain Dew. And he talked about how do we prepare then what's called a 1 molar salt solution. And he went through that as well as an example. So back to your packet, and in this section, you're going to examine several common ways of expressing concentration, including mole fraction. Now, mole fraction we've dealt with before, so we've seen that, and we're going to deal with that again. Molarity is something you've dealt with since Chem 1, and now we have what's called molality. That R changes to an L, and it's going to change our units. So water must be tested continually to ensure that the concentrations of contaminants do not exceed established limits. These contaminants include metals, pesticides, bacteria, and even the byproducts of water treatment. You will learn how solution concentrations are calculated. So pause, fill in those blanks, and then play to hear my words. So these two terms you probably have heard of before. A solution can be dilute, a small amount of solute, or concentrated, a large amount of solute. So mass percent, think about percent meaning per 100 as always. So mass percent is the percent by mass of the solute in the solution. So mass percent would be the mass of our component, whatever component of that solution is, divided by the total mass of the entire solution, and again times 100. So that should make sense. Mass percent, well, what percentage by mass is that particular solute in a solution? So down here we want to remember that percent really means grams though in chemistry. So if something says 30% salt solution, that really is telling us that we have 30 grams of salt in 70 grams of water. Remember, because the 30 would be the mass of the component of the salt, and then the total mass would be 100, right? The total mass would be 100. So out of that 100, 70 grams of it would be water. So we want to kind of keep that in the back of our head. There are things called ppm and ppb. That just means parts per million and parts per million. Parts per million and parts per billion. I'm sorry, I want to make sure I did my million and my billion correct. So what does this mean? You're going to do exactly the same thing, but instead of multiplying it by 100, you're going to be multiplying here by a million and here by a billion. So see if you can do your calculations and then play to see the answers. Hopefully you got that. And hopefully you got that. And again, notice the sig figs, 0.00023, and the reason for that space is because just to show you that there's 3 zeros. Sometimes if you put too many zeros and numbers together, it gets a little hard to see. So I apologize that. I probably should have said that in the beginning, but 0.00023 would be 2 sig figs. So here's 2 sig figs and 2 sig figs. Mole fraction, you've seen this before, the amount of moles divided by the total moles of the solution, right? So we have our moles of component A divided by the moles of component A and B, same thing here. So if we take something like EG, which is ethylene glycol, is added to water as antifreeze, and the portions are shown here. So we have 1.25 moles of the EG to the 4 moles of the water. A mole fraction is the ratio of the number of moles of one substance to the total number of moles of all substances in that solution. So if we look at here, we have a total of 5.25 moles total between component A and B. So we take that mole fraction here, we take that mole fraction here, and what would be the sum of all the mole fractions in that solution? So first of all, usually we don't keep these as fractions. We would equal these out, but what would be the sum of these two? Well, hopefully you mathematicians would have gotten the answer of 1. Okay, so of course a mole fraction, anything with a fraction, we're going to, it's all going to be equal to 1 when we take all of those components together. Molarity, you already know. We want to remember that the symbol is a capital M. You want to remember that it's moles of solute per liters of solution. And remember, when we talk about liquids, we can also do an M1V1 equals M2V2. So here's some practice problems. Pause, see if you can do these, because these are molarity problems, and you should be able to get these. Here's your answer to 1. I did it the molarity way, if that's what you want to call it. I did the molarity way. Or you can also just straight up do it the dimensional analysis way. So it's up to you how you want to do that, just canceling of the units. Here's number 2. Hopefully you got that using that M1V1 again. So now what is molality? This is a little tricky. This is like a cursive lowercase m, okay, cursive lowercase m, and this is going to be important in a chapter, in a section or two. So this is moles of the solute per kilogram of the solvent. So moles of the solute per kilogram of the solvent. So again, this is not too popular. This molality is not too popular. It's not used very often, but it will be used in our boiling point elevation and our freezing point depression, which will come in, again, like I said, in a section or two. So give this some thought, pause, read, see if you can come up with one of these as the answer. Hopefully that makes sense. And again, if it doesn't, I'm glad to explain it more in class. So when you're converting your units, again, a lot of it is just converting units, you might need to use molar mass or density in order to convert from one form of concentration to another. So in other words, here's a nice little flow chart. So when we're going from mass to moles of the solute, you know you need molar mass, right? So that's simple, that we've done that before. However, when we're talking about the solution, you might need to go from mass of a solution to volume of a solution in order to get the molarity that we want. So here, they have to give you the density then, the density of that solution that you're talking about. So if you look on page 529, maybe not now, but maybe when we do our book problems, you might want to take a note and just look over sample exercise 13.6 to get an idea of what I mean. So you have some practice problems to do. Again, if you'd like, pause the video, try to see if you can do those practice problems, and then play the video here and see the solutions. I do have them nice step by step, so you can also pause the video as you go. Like if you're stuck, so you got so far and you got stuck, you can pause it there or play it until you get to that point. So number 1, read that over. We're looking for molarity. Solution. Hopefully that makes sense. And again, what are we looking for? Moles per liter. Okay, number 2, mass percent. Okay, so here's our kilograms. We want to remember that 1,500 milliliters of water really means 1,500 grams. Milliliters and grams of water are the same for our purposes. Now, we know that the density does change depending on the temperature of water, but for the most part, we can say that 1 milliliter of water equals 1 gram of water. So hopefully you got that as an answer. Mole fraction, we've done this before, so can you do it now using solutions? And if you add up 0.238 plus 0.762, you would get the answer of 1. Molality. Now remember what molality, remember what those units are and what you're solving for. And there you go, 0.060. Again, two sig figs because of the 5.0. Okay. See you in class and to work on more practice problems in your book.